In the previous episode we saw how an electric transformer works, a component capable of raising or reducing an input voltage, and thus having greater control over the power that we deliver to our devices. I also told you about a whole series of variables that affect its efficiency, although I didn't mention toroidal transformers, which have some details in their design that are quite interesting. So this video will be dedicated to them. But before analyzing them, let's do a little summary to make sure we have a good foundation. The first thing we should know is that a current can induce a magnetic field, and that a magnetic field can induce a current, with which we can basically transmit power wirelessly, which by the way can be amplified if we use a spiral or coil shape. More specifically, we will talk about a primary winding through which current enters and a secondary winding through which the current comes out. The second thing is that, for this energy to continue being transmitted, we need to use alternating current, because an output current will only be induced if the magnetic field is changing over time. This is also known as Faraday's law. The third thing is that the function of a transformer, as its name says, is to transform the voltage and current going through it, but at the same time maintaining a relatively constant nominal power. Moreover, this transformation relationship directly depends on the difference of the amount of turns between both coils. And finally, the fourth thing we should know is that there are many types of cores which allow us, given its high magnetic permeability, to increase the magnetic flux generated by the primary coil, and as a consequence, to also increase the efficiency of the transformer, since basically this magnetic flux is the bridge that allows the transmission of energy between one coil and the other. But transformers like the ones I showed you in the previous chapter still have certain limitations. And that is why in this chapter we will see how a toroidal transformer works. We will start by analyzing the obvious: why use a toroidal shape? This has to do with the shape of the magnetic field and flux generated by the primary coil. If we have a straight wire, the magnetic field will take the shape of a cylinder, and the magnetic flux will be perpendicular to the direction of the wire, basically forming a circle. Understanding that the magnetic field refers to a representation of the volume that is being influenced by the current that is inducing it, and the magnetic flux refers to the direction of this field at a certain point in space, which we could associate with the direction on which would point a compass if we put it at that same point. Now, if we use a coil with an air core, we will obtain as a result a magnetic field of toroidal shape that expands in all directions, and whose magnetic flux passes through the center of the coil, leaves and re-enters through the other end. If we add a core to this same coil like the one with the shell-type transformer, this will serve as a guide for magnetic flux, and therefore we could say that we now have a magnetic field in the shape of two toroids. Even though the mere fact of using a core will already considerably increase the magnetic flux, this design is not optimal, because the induction effect on the secondary coil occurs mainly in the center, where the coil completely surrounds the core, that is, only a limited section with respect to the total available area. On the other hand, if the nucleus has a toroidal shape and the coil extends completely over it, the magnetic field again will copy the core shape, and the magnetic flux will always be inside the primary coil. And it is precisely this that makes toroidal transformers generally more efficient, and that they may have conversion characteristics comparable to those of other transformers, but in a more compact size. Furthermore, since the core is being completely affected, eddy currents induced by the primary coil in the core are greatly reduced, which also results in a lower operating temperature than other alternatives. But this is not all about toroidal transformers. We haven't even talked about the secondary winding yet. So let's take a look at how a toroidal transformer is made from scratch. First of all, we will have a toroidal core which generally has a coating such as a nylon cover to prevent it from having direct contact with the primary winding. Then, a series of layers are added on the primary winding to avoid direct contact and transmission of electricity with the secondary winding. Finally, after covering the set, two washers are usually added with a rubber separator to avoid damaging the cables, a bolt, and a nut, which together work like a press to hold everything together. An important detail to keep in mind about the configuration that I just showed you is that the primary winding has more turns than the secondary winding, which means that it is a voltage-reducing transformer, but the logic is always the same. The output voltage will be equal to the input voltage multiplied by the division of the number of turns in the secondary winding and the number of turns in the primary winding. And although it is not a characteristic exclusive to toroidal transformers, it is common to find some of them that have multiple current inputs and outputs, which makes them extremely flexible for different uses. To exemplify this, we are going to need a little math, but nothing out of the ordinary, so don't be scared. Let's start assuming we have a primary winding with 100 turns and a secondary winding with 10 turns, that is, a ratio of 10 to 1. Only with this, if our input alternating current were 220 volts and 1 ampere, it means that the alternating current output would be 22 volts and 10 amps. Of course, assuming the transformation efficiency is 100%, which is not true, but why make things complicated? Now, if we add a second secondary coil, this time with 20 turns, we would have a new output of 44 volts and 5 amps. Although remember that the nominal output power will never be greater than nominal input power. Even though now we would have two possible voltage outputs, this design can be simplified, since we will have 30 turns and 4 output cables. What we can do is merge both secondary coils in one. That is, leave only 20 turns, and add an extra cable right on the 10th turn. If we use the first and second cable, we will get 22 volts, and if we use the first and third cables, we will get 44 volts. This means that we achieved the same results with 10 less turns and 1 less output cable. Furthermore, this logic can also be applied in the primary winding. If we had a connection at 50 turns and another at 100 turns, but we still use the 220 input volts, now we will have 4 possible output voltage combinations: 22, 44, 44, and 88 volts. But this is generally not the reason why multiple primary coils are often used. Its real utility is when we have a different input voltage. If we use this same transformer with an input voltage of 110 volts, we can use the primary coil with 50 turns and get exactly the same output voltages as with the 220 volts. We could take this to the extreme and add more sections of the primary coil and the secondary coil, obtaining dozens of possible combinations, but the concept would remain the same. I repeat, this is not something exclusive to toroidal transformers, but it seems important to mention it because many of them use this configuration. Now that we understand all the benefits of toroidal transformers, the question is, why don't we use them everywhere? Unfortunately, not everything is perfect, because, due to their shape, these are usually more difficult to build than other types of transformers, which implies that they usually have a higher cost, and that generally are not usually found in very large sizes, limiting the maximum powers to which they can operate to only a few kilovolt ampere. I also remind you that if you want to support me on making more videos like this, you can also do it through Patreon, where you will get early access to the videos, 3D models, and even your name in the credits. That is all for now, and see you in the next video.